I don't know if Amanda is going to join today or not, but we'll find you. Yeah, we'll find you to chat about this. Yeah.
Thank you.
Okay. Cool. Yeah. Next. Cool.
Hi, I'm Zen. I'm working in Liang Seminar Academia Syndicate, and so my interest right now is mainly on quantum computing, and then we have and also some topology work. I think maybe Liang Xing mentioned to Fuliang feature spectrum topology, and then we're also interested in machine learning, maybe applying it to various DFT correlated systems as well, or maybe some machine learning plus quantum computing hybrid. So that's our interest right now. Thanks.
Yeah. Next. Karen, do you want to?
Sure. Hi, everyone. I'm Karen. I'm entering my last year of undergrad at MIT, and I've been working with Liang on some condensed matter problems concerning the ground state of the ferromagnetic Kondo lattice model. But I'm also interested, like everyone else here, in learning more about AI and machine learning for condensed matter physics in particular.
Thank you. Yeah. Next.
I can go. Is there an order to this, or
Yeah, doesn't matter.
Okay.
Yeah.
All right. Yeah. Hi, everyone. I'm Aiden. I'm a third-year PhD student working with Liang at MIT, and so far my interests have mostly been in Moiré materials and fractional quantum anomalous Hall effects in Moiré materials, using numerical studies, mostly exact diagonalization, to understand the quantum phase diagram of these systems. So nice to meet you all.
Hello everyone. I'm Angus. I'm currently working with Professor Benzel at Northeastern University. I'm third year in my PhD. I'm mainly working on DFT stuff and machine learning. I've done some project on the learning the ground state wave functions of 1D Heisenberg model using the transformer. Also done some machine learning on the DFT, which is on the material, combining them together. And that's like the project I'm working on right now. Nice to meet you all.
And Xing, you want to say something?
Hello, my name is Xing Lin. I'm at Academia Syndicate in Taiwan. I work on DFT and topology. And and my group recently started working on machine learning and quantum computations. Okay, nice to meet you.
Great. My Zoom is got stuck. I may need to log in again. Yeah, give me a second. Sorry about this. Know why?
My turn. I'm Baohui. Can you hear me?
Yeah.
Okay.
Yeah, you're good.
I'm a PhD student in Taiwan, and I will be in Professor Lin Xin School in the future as a as a postdoc. And I'm working on DFT and spintronics. And in the future, I will study the spintronics quantum chemistry in quantum computing. And I'm also interested in programming and machine learning, something like that. Yeah, nice to meet you.
Yeah, nice to meet you.
I think that's everyone except for Nipun. Is that right?
Um, Hello, everyone. I'm Vina. I'm an undergrad, and I'm working with Koch to approximate atoms using different quantum Monte Carlo methods using Fermi-net and Poly-net.
Okay, great. Yeah, sounds good. Yeah. So yeah, should we start? This is hopefully we want to hopefully get enough people to talk about their work, or could be a journal club and something like informal meeting. Hopefully, we have that every week. Yeah. And today, it's a great pleasure to welcome our 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 visitor, Abhinav. Yeah, remote visitor.
Yeah. So I'll start sharing my screen. So
Yeah, sure. Yeah. By the way, these talks can be very informal, and feel free people to interrupt and ask questions, and this is really to get all of us to think more about interesting projects and collaborations and etc. Yeah.
so so in this talk, I have a short PPT. So I've been thinking about some problems where I can apply transformer models to solve uh, like problems in quantum chemistry. So I'll briefly talk about the problems which I've been thinking about, and then project which I'm working on. So the problem, so the basic problem, right, which the problem which I'm currently working on is the famous ground state estimation of a Hamiltonian. So the problem is basically given access to like a Hamiltonian matrix and compute the ground state and expected ground state energy. And for solving this one, several methods exist. One would be like quantum phase estimation based methods, but that would require like fault tolerant quantum computers, which we do not have. Another famous one is like variational quantum eigensolver. These are feasible on near-term quantum devices, but uh, they do have barren plateau issues, and so they do have some limitations around that side. So so the main idea which I was thinking about was to like reduce the ground state estimation to like a sequence generation problem and apply foundation models to compute representations of ground state. So let's say if I'm given a Hamiltonian edge, so our goal would be to like generate the quantum circuit that prepares the ground state. So like more precisely, we are interested in modeling this probability distribution, which is like given a Hamiltonian, what is like the expected ground state, and I can represent the ground state uh, as a sequence basically. So the idea is I can given any quantum multiply ground state can be represented as a unitary matrix acting on the on let's say on the zero state. And then the unitary matrix can be decomposed into like a finite set of gates. So then the ground state prediction problem can be reduced to like predict the gate sequence given a Hamiltonian edge.
I'm
So
sorry. Yeah,
yeah,
Abhinav. So
yeah.
the distribution you're interested in, it's the probability of psi acting on H. So it's
So
expected some expected eigenvalues multiplied by some expected eigenvectors. So it's a probability distribution of some it's a probability distribution of the eigen of some, I don't know, some approximate eigenspectrum times some approximate eigenvectors. Is that right?
yeah, yeah, it's
What's the
mostly like
distribution?
it's a distribution of like a vector. Uh, so psi is here like is like a high
No,
dimensional
no, no.
vector.
So okay, but put it away. The distribution, is it a distribution of the eigen of is it probability distribution of the eigenvectors, or is it a probability distribution of the eigenvectors acting on the Hamiltonian? So yeah.
Uh, it's the probability distribution. I would say the eigen values. Let's say if I have an eigenbasis, if I know the eigenbasis for this piece, then my goal would be to like compute the eigenvalues. But I'm representing the ground state as, let's say, quantum circuit acting on a unitary matrix uh, multiplied by, let's say, the zeroth state. So this is like a sequence of quantum gates. And if I can predict the sequence of quantum gates, then I would get a representation of the ground state. So that's the basic idea.
So the probability distribution is over the gates.
The sequence of the gates. Yeah, it's over the sequence of the gates.
Okay.
So it's kind of like predicting the sequence of text given some input. So so the idea basically then is that you can solve the sequence prediction problem by using like vision language foundation models, and the Hermitian matrix can be represented like a 2D image, and then the gate sequence can be predicted using like vision language foundation model. So one example for this one is like Pali Gamma. So this is like an open source model from Google. And basically this model is for predicting, like given an image and a given like a text prompt, it would give like a description of our image, or you can answer questions about the image. So we can apply the same idea for like quantum problems. So the idea would be to like represent the Hamiltonian matrix as some black and white image, and then the input text would describe the problem that you are interested in. So it could be predicting the ground state of the Hamiltonian, and then the output would be the gate sequence representing the ground state. So it would still be like a compressed representation of the ground state, because because it might be really unfeasible to represent the ground state using exact representation, but it would still be like a gate sequence representing the original ground state as an output. And
what is
so
the
that's
state
like,
zero? In your previous slide, you say that the ground state is what you get from acting with some unitary operator on some state zero. What is that state zero?
so state zero, I meant like this one, a tensor product of, let's say, basis zero basis states. So by state zero, I meant, oh, maybe I can write it here. Yeah, so basically a vector of, basically a basis vector.
Okay.
Yeah,
so just some randomly chosen
yeah, it could
basis
be
state?
Yeah, yeah, randomly chosen basis state. So I just chose it to be like state zero.
Wait, isn't this zero normally just mean your starting state of like quantum computing? So like let's say
Yeah,
test
yeah,
products of all like sigma z
yeah,
basis, or something like that. It's
yeah,
just
yeah.
weird.
Yeah, so I meant the starting state in the quantum computing. So that's what I meant. So zero, let's say zero tens. So basically, the ball phase zero would denote zero tensor, zero tensor, zero tensor, zero. So it would be basically the starting state in a quantum computer.
Okay, so like no matter what Hamiltonian you're dealing with, that will always be your starting state. They're fixing that.
Yeah, so basically zero tensor one would be like 1 0, and zero tensor n would be like basically you'll have like a vector with one at the top and then zeros everywhere.
Okay.
Basically the quantum initial state in a quantum circuit. So that's what I'm. And then the approach would be to like apply, let's say I have a Hamiltonian matrix, I can use that like an image input to the gamma model. And then I could have like different tasks. Let's say it could be ground state prediction or first excited state. And then I could train the gamma model to generate a desired, let's say, output. And the output would be in terms of like a gate sequence representing the quantum state.
I'm sorry.
And
I'm not too familiar with the vision language foundation model. Can you sketch its architecture?
so basically for a vision language foundation model, you have like a image input, and then it goes to like an image encoder. And they do have, after that, there is like a linear projector acting on the image input. And then for and then it would also take a text input. And then
Wait,
basically
sorry. So you code the image as a 2D matrix, and then you feed it into an encoder, okay? And then the linear projection is
yeah, so the linear projection would reduce the dimension to the dimension of let's say a token space. So the text input would be mapped to like a token space of uh, dimension RD, but the image necessarily need not be of that dimension. So the linear projection would basically map it to that dimension space. So it's basically like a projector to reduce the dimension of the image.
okay, thanks.
So with this method, again, you need a lot of training data, right? And
Yeah, yeah.
this is and you're not guaranteed that the answer will be correct, right? There's no guarantee the answer when you apply it to a new problem. There's no guarantee the answer is correct. It kind of right. It kind of relies on the sort of the magic of right, the magic of neural network to do everything you asked it to, right? Kind of
Yeah, yeah, kind of,
right.
true.
Uh-huh.
Yeah, but
Okay.
if you, yeah, but the idea is if you train on enough, let's say, diverse samples, and if you have like a, if the
Right.
network is generalizing, then it would basically,
Yeah, but again, it's
model,
sort of it's kind of
yeah,
on shaky grounds, right? Because this is if one of the things about science is that we want an answer that is exactly correct, right?
right, yeah,
So in that sense, it's a bit of a shaky grounds.
yeah, that's true. I mean, yeah, you cannot. I mean, you cannot really say this is exactly right. Yeah, that's true.
Right.
Yeah,
Okay.
yeah.
Why don't
Uh,
you finish? Yeah. I'm gonna finish this.
sorry, sorry.
Yeah. Go ahead, Ben. Yeah.
E- Uh, 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 no, no, you could have a reinforcement learning reward function acting on to minimize the ground state. So the reward function would be the predicted ground state energy. So you could have that as well. So you could train. So you could basically train this model either with like a supervised synthetic data which you have, where you actually exactly compute the ground state and use the network to model it. So that's one approach. The other one would be to use basically reinforcement learning to basically to take this representation and compute the reward from this one, and then use that to like use that in like use that like an RLH of objective function to train the model.
Okay. So if I understand correctly, what you are saying that you give it a Hamiltonian matrix as an image, right? It give you a gauge sequence, and then you are saying that I can then calculate the variational energy, right, of such a ground state. And that is, telling you, if you know given me another sequence, give me another ground state, I can also look at the variational energy. So in this way, it's more like optimization, right? I can.
Yeah, it's more like optimization. Yeah, it's more like optimization. Yeah, you could basically then train a reward model to. I mean, you could basically use reinforcement learning methods to optimize the parameters of the transformer model here.
Okay.
If I don't have the, let's say, synthetic data. So
Okay.
yeah.
So that make it more like a variational method,
Yeah, it's
which
more like a variational method, but the only
is
difference
better, in
is
my opinion. Yeah.
yeah, but the only difference is you are not restricted to like a fixed ansatz. Since you can since the transformer model can model arbitrary gate sequence, so uh, you'll be able to represent more quantum states with this sort of model. That's my sense.
Yeah, I mean, this may be related to my question. So, if you think about variational method, it's it's important to have a big expression, the variational wave function, right? Ideally, you want to have a very, you want your method to be able to produce a large class of variational wave functions, right?
Right,
So
right.
here the wave function are represented in terms of a sequence of gate operations,
Yeah.
and I guess in principle, if the gate operation is very long, right, sequence is very, very long, then in principle you can cover any wave function. Is that the idea?
Yeah, that's the idea. That's the idea.
Okay.
Yeah. So that would be, yeah, because in that sense, so this would have like more representational power than like a variational optimizer where you like fix an ansatz and then optimize the parameters. So that's
So here, in
that's
some sense, the variational parameter is represented as a set of gate operations. Right?
yeah, in some sense, yeah.
Right.
But the gate operation could be like a universal gate set. So
in principle, it can represent any state.
yeah, in principle can
In
represent any
principle,
state.
right. But then, how efficient is it to evaluate the energy? Right? If you represent the variational wave function using a sequence of gate, right? Then to calculate the expanding value of the Hamiltonian, how easy, how hard it is.
Yeah, that could be a harder problem to evaluate the expectation energy.
Right, that might be hard. Right.
Yeah, that may be a harder problem for larger matrices. Yeah. So yeah.
Right.
Yeah.
Right.
I mean,
Right.
can I have a question? So like if like you say it's basically like the way I understand is that you have some sort of architecture, which I don't know what exactly the architecture you have, and you may have like several layers of gates or like some sort of network with variational parameters that you can optimize. And then so after you like create a state, let's say there you have a Hamiltonian like with different terms that do not commute with each other. How do you then get the expectation energy of this Hamiltonian?
Can you just repeat that again, please?
Like, for example, if you were to do like a system like Tory code or whatever, something similar, like you have different terms in your Hamiltonian that do not commute with each other, right? So like, I don't know, maybe I'm not expert on like quantum circuits, but like based on my experience, it's like very hard to make like measurements of those variables when they do not commute with each other, on an actual quantum circuit. Like if
True. I mean, the measuring the expectation value of energy can be hard for let's say if I'm using like an actual quantum circuit.
Yeah.
Right.
So how do you do it actually?
I mean, if the Hamiltonian matrix does not commute, there are some methods to do it. Like you can use some LCU based techniques to do that. So there are ways to get around it. Yeah, but I don't have that detail in this presentation.
Right.
Yeah,
Yeah. Okay.
I skipped all that. Yeah.
Right. Okay. Could you wrap up? Yeah.
Yeah. So I think Yeah, I think the hope would be if the foundation models can possibly like generalize to higher dimensions, then this would be like a feasible approach. Like if I have, like if I can train on, let's say, n equals 3 to 4, or like smaller dimensions, and if it generalizes well, see if this thing generalizes well. I think the main advantage would be that we would be able to like represent complicated ground states since we do not restrict ourselves to like a specific choice of answers, and possibly could be used for other tasks at, let's say, first excited states or something,
Mhm.
along with ground state let's say prediction. So it could be like a single model that can possibly do larger tasks. But I agree the training could be like really expensive. So I'll think
No,
I
but
have to
also I
think.
think it's more not just training part, right? If you use it as a variational method, I mean, I agree with you that any wave function can be represented as a sequence of gates, right? Universal set of gates acting on some reference state, right?
Yeah.
But then, in other words, then you can use a set of gates to represent a variational wave function, right? That I have no problem. I'm okay with that. But then it seems the challenge is how do you actually evaluate the expanding value of Hamiltonian efficiently, right? Is it obvious you can do that efficiently?
For some class of Hamiltonians, yes. If I restrict, let's say, if I restrict to Heisenberg models or something like that, then there could be ways to
But is that
evaluate.
it's obvious? I mean, you have a sequence of gates operating on the reference state, right? And you have to evaluate the expectation value of Hamiltonian. Is it obvious that's easy to do? I'm not sure, to be honest, because the method I know is like, if you represent, your wave function using a variational wave function, it's within some basis, right?
Right.
Then, explicitly the um, the the amplitude of wave function for every configuration, right? Then you can evaluate the experimental Hamiltonian. This is variational Monte Carlo methods. But here you are representing everything in terms of a set of gates operating a sequence of gates acting on some reference state. It's not obvious
Right.
to me that you can actually evaluate the experimental Hamiltonian.
You can use the Hadamard test in quantum circuits to evaluate that.
But are you assuming, in other words, maybe you're assuming if you have a quantum computer, you can do that. Maybe that's the whole motivation of what they're doing, right? You're assuming
Yeah.
that you already have a quantum computer.
Yeah. Yeah. Then, I mean, if you have like near-term quantum computers, then you can do that. Yeah.
Fine. But okay. That's okay. That's not sort of what.
Yeah.
Okay, that's
Yeah.
fine. It's not something we
Yeah.
are. What I've been thinking is something different, right? As I told you
Yeah. 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 True.
yeah.
Yeah.
Because to me, yeah, okay, yeah, okay, good, yeah, thank you. But we can. This is
Yeah.
not
Yeah.
brainstorming and
Yeah.
just chat. Yeah,
Yeah.
I
Yeah.
feel like before we get any useful quantum computer, AI will solve the problem for us, right? Classical
Yeah.
AI is classical computer because it's so powerful, right?
Yeah.
It's so
Yeah. True.
cool. We don't have any good quantum computer used anything useful. I think we are far away. Yeah, right. But AI is already becoming so powerful. Right. So that's why I personally is very excited about using AIs to solving quantum problems. We don't want to wait for a quantum computer to solve our quantum problems. With existing AI, we can already do a lot, I think, to solve quantum problems. Yeah.
Yeah. That's true. So
Okay.
coming to the expectation value, I mean, computing the ground state energy. I mean, there is one way to do that where you also learn another model to like represent the, let's say, ground state energy. I mean, you learn another model which can compute the ground state energy of the wave function given a gate sequence.
Yeah, but
So
again, that how much of that is
that
is accurate?
again,
Is really accurate.
yeah, the accuracy principle would again come there. Uh, but I think most of these machine learning problems, you just try training them and then see if the method works. That's like the approach we should take.
Okay.
And most usually, like if you train on enough diverse samples, they generalize. So you can, I mean, you wouldn't get like a accuracy guarantee in principle, but you could say the value is close to this one. Yeah.
Yeah. Okay. So maybe this is where we can I can say a few words, right? The reason that I'm very excited about all this FermiNet, right? FermiNet type of architecture, and also there's a recent paper using the transformers, which I don't understand. But I can say a few words first about this general idea of the FermiNet, right? Some of the people in the audience get interested and carry out their own implementation of it. This FermiNet idea is really just a variational Monte Carlo, right? So what variational Monte Carlo means, I think we write down some variational wave function in some basis, right? And we evaluate the expected value of Hamiltonian, right? And then we try to minimize the total energy, right, over variational parameters. So this method is, right, traditional many-body physics method, right? Ever since the start of quantum mechanics, people use this all the time, variational wave function method. So what does neural network brings us, right? My understanding is just that, and for example, let me first give you some example about this. If you assume your variational wave function is a slated determinant, is a single slated determinant, then this variational calculation is called the Hartree-Fock method. Right? So the Hartree-Fock method is the same as variational calculation, assuming your ground state is just a single slated determinant of a certain set of single particle orbitals. Right? That's why you should think of Hartree-Fock as a variational method. And the variational method is guaranteed to give you an upper bound to the energy, right? If you have two different variational methods, and one give a lower energy than the other, then we know the first method is better. So everything is rigorous, right? Is rigorous. Okay, so what FermiNet does, right, is that it produces a very large family of variational functions, okay, for fermions. And the idea is very simple. The variational wave function takes the form of a slated determinant. Can I annotate somewhere? Yeah. Can people see my writing?
Yeah.
Right. So the usual state determinant is like this. A labels orbitals, a set of orbitals. I labels the number of particles, 1 to n. Right? So phi A R I is a square matrix, and you can take the determinant of that matrix. So this guarantees the many-body wave function is antisymmetric. Okay, when you exchange the coordinate of two particles. Okay, this is a simple variational wave function, which is a single slit determinant. So what FermiNet does, right? And it's just it generalizes this into the whole set of particle coordinates. Okay, instead of each wave function phi a depends on only one particle position. Each phi a function depends on all particle coordinates. Okay, very simple, right? So this, again, the nice thing about this wave function is that it's guaranteed to be antisymmetric. If you exchange any two particle coordinates, it changes sign. Okay, so yeah, and then this whole FermiNet is based on just optimizing this many-body, that's sort of the basic idea, using a neural network to represent the wave functions of this type.
Right.
That's the idea of the FermiNet. And it's a variation method, so it's fully rigorous.
So Liang, I actually have a question. So in the single site determinant, the indices of the matrix are okay. For the single site determinant, the indices of the matrix are A and I.
Yeah.
But for the Fermi ansatz, there are many I's.
Yeah.
So it's a higher dimensional. It's not like
no,
not
it's
just a
still
matrix.
fine. I don't. Initially, right, you have n row and n column, right?
Yeah.
Right. And now you still have n row and n column. I think it's just every wave function, right? In here, it depends also on the coordinate of other particles. I mean, maybe Cash and others can jump in because this is sort of the basic idea I know of.
Okay. Yeah.
But other people know better. Right, right. And very good. Right, right.
Mhm.
Yeah, right. Yeah, absolutely. So catch, yeah. Let me catch made excellent point. Let me maybe say a few words first, just on top of what he said. I think as the mathematical rigorous statement, one can prove that this can represent any wave function. In fact, this has to be true because imagine this matrix just a one by one matrix, and this psi itself already contains all possible manipulative wave functions, right?
Right.
Sometimes
Yeah.
it's guaranteed, right? But this is useless, right? Because the point is that if you want to generate a function that is very very complicated, if you have a finite depth of neural networks, right? It's probably not possible, right? Or even if it's possible, taking infinitely long time or something. There's the issue of being practically useful. So the experience I've had, working on many problems in this direction with the law is that. So, for example, if you want to use neural network to represent the wave function, which is highly singular, right? Then it's challenging. If you want to represent the delta function with neural networks, it may be challenging. But then what you should do is, the Fourier transform of delta function is very simple, right? Then instead of representing the wave function itself, if you know your wave function has a sharp peaks in real space, you actually want to re-express the wave function as a sum of Fourier components and use neural network to get a set of Fourier components. Instead of trying to
Yeah.
represent f of x, you write fx as e to the I qx f of q, and you use neural network to generate f of q. Okay, this shows up a lot of times. So another example is that again, this kind of wave function in principle can also represent the wave function of the superconductor, the BCS wave function. In principle, you can rewrite your BCS wave function in this way, right? But then this function will again be very singular. Okay, so then actually the DeepMind company, they studied this problem. They found that if you have only a few particles, okay, let's say less than 10 particles, if you just use this architecture, the neural network can still get the right answer if you find a pairing. But if you go to 20 particles, then it becomes practically not possible. Okay, so then both DeepMind and us, we came up with a different way of the neural wave function, which is more like the BCS form. Okay, and then we can easily extend it to problems with pairing, right? So in other sense, the more physics insight you have, right, the better you have, the better you can
Yeah.
design the functions. So I think there's a lot of interesting opportunities here. Yeah. So that's why I think at the very minimum, you can think that wave function of this type, right, should be very as a practical thing. If your system is close to some mean field, if your ground state is close to a mean field state but has fluctuations, right, then you're pretty much guaranteed that using neural network it can be very successful, right? Because at the mean field level, the single state determinant should work. It's qualitative correct, but it does not capture enough fluctuations. It may make the energetics wrong, right? So then you use this Fermi-net, it can give you the good energetics. Yeah. So these are I think all interesting things to explore. Yeah. Yeah.
Yeah.
Yeah. Does it make sense? Yeah.
Yeah, makes sense. Yeah.
Yeah. And people tried all kinds of this from DeepMind. They tried all kinds of atoms and molecules, right?
Mm-hmm.
Calculating the energy, have a lot of success. Yeah, so I think that's the example that those things could be very useful. Yeah. So yeah, Catch, how much you have tried to actually get the code to work, or or your own code or whatever. Yeah. Right. Right. So for all of you guys, if you guys are interested, I think a simple problem that is experimentally relevant is the following. You think instead of about three-dimensional systems, you think about systems in low dimensions, 2D or in one, because nowadays we can make nanowires right out of semiconductors. We can get 2D materials which are just atomically thin. And in these systems, there are all kinds of exciting experiments going on, right? For example, right, take two layers of semiconductors, TMD, you twist them, you create amazingly, ferromagnetic, spontaneously quantum Hall states, even the fractional ones, right? You twist them at some filling, you get superconductivity, right? These are really the true frontier of condensed matter physics nowadays, because the element is so simple. It's just a semiconductor with parabolic bands, right? And you do something to it by applying a twist or forming a moire, you got all kind of magic. Right? And I think that's this kind of a Fermi net, this kind of a neural network methods will have enormous uh, opportunities for finding new phases of matter, for understanding phases of matter in these 2D materials, 2D and 1D materials. So one of the simplest thing, right? One of the simplest thing to work on is just a few body problem. Instead of solving many body problem, let's think about just a few body problem of one electron, one hole, and they will form a bound state called exciton, which experiment has observed many times. But now, with collaboration with our Berkeley group, we are studying multi-body bound states consisting of m electrons and n holes. Right? M and n can be equal or they can be different. Okay, so these objects, are the solid state version of molecules, right? In the real molecule, you have electrons and nucleus. Nucleus carry positive charge, electron carry negative charge. But nucleus is essentially infinitely heavy than compared to electrons. You treat the nucleus as immobile classical particles. Whereas in semiconductor systems, you have electrons in conduction band, you have holes in the valence bands. They have roughly similar effective mass, right? So this is like a positron and the electron bound states, right? It's like the positron hydrogen, right? Or positronium or whatever, yeah, right. So now experiments are just starting to detect these multi-particle bound states. And the experiments, they asked me a long time ago, can we calculate bound state energy? Right? And I think this Fermi net methods, these neural network methods, will be a great starting point to look at these few body bound state problem. Does that make sense?
Yeah, that makes sense.
Yeah. So, one thing that Cash, I think, yeah, again, yeah, I think, or anybody, yeah, anybody in the audience, if they're interested, yeah, if we start with this, just these few body bound state problems, I think this will give us a handle, right, on how the neural network actually works, how it actually works, right, how that works. Yeah, this could be a good sort of a starting point, yeah, for investigation. Yeah. Okay, sounds good. Any other ideas? Any other thoughts?
No, I don't think so. Yeah.
Okay. Anybody else? Yeah. Okay, sounds good. Yeah. So we need let's make this more like a regular meeting, and we need volunteers, right? So it doesn't have to be about the original research. It could be just reading some papers in this broad AI for quantum direction. I think it would be important for us to yeah, it'd be good for us to meet regularly. Yeah. So to keep our momentum. Yeah. So anyone want to volunteer? to give some talks next week. What about Cash? Again, it doesn't have to be original research. It could be just give a presentation about some papers some classic papers in the field. Again, this can be very informal. It's also fine, but as long as it'd be nice if you can make some connection with quantum, right? I think that's my only the only boundary condition. This is AI for quantum. Yeah, the reason of course, there's enormous application of AI for non-quantum applications like ChatGPT. I just feel like I don't see myself contributing much, right? But I do feel like sort of the last job I like to tell people, right? Tell my students, the last job to be replaced by AI is quantum physics, because quantum problems are intrinsically hard, right? Intrinsically hard. Yeah, there's no other things, no other, especially quantum manipulated systems, yeah, intrinsically hard because of the exponentially large Hilbert space dimension. Okay. Yeah. So that's why I think we are the last to be replaced. So that's why. And you can see that you cannot just blindly do the AI, right? In this example, sensitivity is very clear. You can try to say, oh, there's a universal representation theorem. All wave function can be written as just this generalized slated determinant. But practically, it doesn't work. Okay, it doesn't work for superconductor. So that's a beautiful example showing that the more physics you have, the physics knowledge you have, the better you can design actual neural networks that can work. Yeah. So there's a lot of interesting things here. Yeah. So combining quantum physics is, yeah, that'll be a good thing. Yeah.
If you to have this Fermi net wave function where you have this determinant of many particle wave functions, like presumably you can go very far by only making each of those functions depend on like 2 or 3 particle coordinates at a time, et cetera,
Absolutely.
right? So
Absolutely.
when you have many particles, that
Absolutely. And in fact, many of the for many of the states, right, that in the end, I think that if you work, when it works well, when it works well easily, it's probably that each of these generalized state determinants are still very close to the original one body, right, orbitals, but it may involve a few particles. In fact, sometimes it only involves a few particles that are nearby. Yeah, this is the idea of the so-called backflow idea. That's so this is not the in other words, this wave function does not come from DeepMind. In condensed matter community, people already thought a lot about this kind of dressed single particle wave functions. It's like a single particle wave function dressed by nearby electrons. This actually started with Feynman. Feynman was called the backflow idea. Yeah, it has a long history. Yeah. So I'm saying that you see this. That's why I think this is a great example. Right? You have to really combine AI with physics knowledge to solve physics problems, right? Especially quantum physics problems. Yeah. Right. Yeah. So So catch. Yeah. So to get back to your question, it doesn't have to be it does not have to be original research. It could be any paper that you think that's relevant, as long as you make some connection with quantum. One important thing is you meet regularly, so keep the momentum, and then through these discussions, right, we can get a lot of things, started. No, you don't have to seek my approval. It's just as long as you agree to talk on Monday, you can talk about anything you like. Yeah. Shall we put it down for Monday next week? Yeah. Again, don't. It doesn't have to be anything, about original research. And again, the talk can be very short, like 20 minutes, or even less. Yeah, there's no problem. It's just to get all of us to meet regularly. That sounds good. Okay, and also maybe Xing, on your side, is there anybody on your side want to volunteer, maybe the week after next. Unmute yourself, Xing. Yeah. Also, I think we chatted about earlier today, Xing, that feel free to bring other members of your group who are doing, broadly AI or AI for material research, etc. Are you still there, Xing? No? Okay.
Yeah, I'm not sure who will be volunteer to do that.
Actually, one of the group
I can
members.
do the week after next. I can do the week after next.
Oh, okay, sure.
So,
yeah, Aiden. Yeah, okay, sounds good. Yeah. Okay, yeah. So then, yeah, we can keep it going. Yeah, let's keep it going. And actually, Xing, I think someone in your group said, was doing something related to this, the Ferminet or something. I don't know. I saw somebody in your group said.
No.
Is
Not
that Anders Su?
Yes,
Yeah.
that's me. That's me. So yeah, I was working on one of the paper that you sent out, which is the transformer on the
Oh,
they're the Heisenberg model, right?
yeah.
I did a project about that, but unfortunately I couldn't speak too much about it because it's ongoing work. But I can, just go through some details. But based on what we done, it's still a variational method.
Fantastic. I mean, again, you don't have to talk
Mhm,
about unpublished work, but you can talk about something that's sort of already in literature, but something that you feel excited about, right? That's fine.
Yeah, I mean that's like that part I know what to talk or what they're doing. They didn't like write it out explicitly in their works, so I mean I really don't like that paper to be honest.
Oh, this is a paper that I said this J1, J2 model. Is that
Yeah, exactly. The from the Italian group. They
okay?
didn't. They don't have the source code. They don't have everything. They just have the results. Um, so I don't know. I don't know about that paper to be honest.
So who are you working with on this project?
That was like few months ago with Adrian Fegwin, Professor Adrian Fegwin.
Yeah.
We are working on that project, but
Okay,
I'm
sounds good.
not working on that right now.
Okay, perfect. Yeah. So you don't need to talk about any unpublished work, but just just sort of the general idea was already in the literature. But if you can add your insight, that'll be greatly helpful. Yeah, very helpful. Yeah. So yeah, right. Sounds good. Okay, sounds good. So like we have several weeks covered then, right? Perfect. Yeah. Okay. Yeah. Good. Okay. Wonderful. Yeah. Thank you all. Yeah. Have a good summer. Yeah. Okay. Bye.
Bye, thanks.
Thank you.